Delighted to introduce Guy Boyde to talk about classifying vector bundles.
Thank you. Thank you for having me. Thank you all for still being here at 5. And I guess also thank you to the previous speakers this afternoon for keeping the energy so high. But I'll try not to stand between you and your beer for too long. Okay, so we're going to get to some joint work, which is in very early stages, which I'm doing with Miles Daggett. And because it's in such early stages, all I'm going to manage to do is like sketch the terrain that we found a place we want to dig, or maybe make a map of. We're not quite sure what the right way to do this is, what theorems we should try and prove and how to structure it. So we're looking forward to having some conversations about what you all think would be interesting in this regard. But before we get to that, I want to sketch a program which is really originally due to Yang Hu, I think it was his thesis, which explains what calculus has to do with counting and classifying vector bundles. So hopefully this would be a nice thing to take away. So I didn't want to assume too much knowledge of the classical story of what homotopy theory has to do with vector bundles. So let's start there. But I'm sure lots of you know this, so I apologize for the first slide. But this vect sub d of x, this is going to be our notation for the rank d complex for now vector bundles over our favorite space x. And we're going to live in base spaces for a bit. And it's just a fact that there is a space called BUD that represents such things in the sense that the data of a vector bundle over X of rank D up to isomorphism is the same thing as a homotopy class of base maps from X to this space BUD. And better still, one thing you can do with vector bundles is you can take your vector bundle V and you can direct sum on a trivial bundle. So that's one that's just a copy here of the complex numbers over every point in X. And that takes you from vect D to vect D plus 1 because you made the dimension 1 bigger. And that's compatible with a map from this guy BUD to this guy BUD plus 1. Okay, so then you can iterate because that's what we've been doing this week. And I mean, this thing we don't normally talk about, so ignore it for now. I just wanted the diagram to look square. But if you go all the way to the bottom here, then there's a name for the sequential colimit or the ascending union of these spaces BUD, namely BU. And this space is the representing object for complex K theory. So somehow what we learned from this is that you can start adding copies of the trivial one-dimensional bundle to your favorite complex vector bundle, and eventually you land in K theory. K theory is the place that captures the data that survives this stabilization process. Okay, so I've been talking about BUD like it's just some guy, but what is it actually and why is this a good thing to do? So BUD is the classifying space for the Lie group UD, which I looked up on Wikipedia in the 5 minutes before the talk, and that's the complex D by D matrices whose inverse is their conjugate transpose. This is a very down-to-earth thing, but any such thing has a classifying space, and you get back the UD from BUD by taking loops. This will do as an understanding for us for now. So in particular, there's a map from UD to UD plus 1 on matrices. That means put a 1 in the bottom right and zeros in the extra row and the extra column you've gained. And the quotient is a homogeneous space, the quotient of this UD space by the UD action, turns out to be S2D plus 1. So you can squint at this a bit and think about what's happening on bases. And the point is that this S2D plus 1 is one unit vector inside C D plus 1. That's how it goes. And if you continue this sequence of maps, which I'm going to call fibration, meaning each term is the homotopy fiber of the previous one to the right, you get to BUD and then BUD plus 1. So this is really telling you something about that map. And because this S2D plus 1 gets more and more connected as D grows, the map from BUD to BUD plus 1 also gets more and more connected as D grows. And in particular, if you put in a finite dimensional x in the other variable, then once 2D gets bigger than the dimension of x, you find that this homotopy set that we care about has stopped changing. So actually you arrive at the stable version of the vector bundle, the thing that it is in complex K theory at some finite stage. And what we're going to be looking at in this talk, for reasons that will become apparent on the next slide, these are the ones that calculus really adds something to, really give you a way to interpret, is the set of stably trivial vector bundles, which are the ones that don't survive this process. So literally here, I mean the kernel of this map from that homotopy set to that homotopy set, or in other words, when you go from vect d of x to real K theory, the things that do not survive the kernel of that. Okay, so this is classical homotopy theory for vector bundles. Sorry.
Oh, no, I think it's good. Just while we're interrupting, I think there's a tech issue with the sharing. I don't think people on Zoom can see anything. They can also deal with that. I'm stuck in a corner.
Okay. Do you want me to pause for a moment?
He's not stuck in a corner anymore. Very sorry.
It's okay.
It doesn't even see it when you carry on, guy.
I should, okay. Does anyone have any questions though about this, like classical homotopy theory, giving you an interpretation of vector bundles as maps? And there is a whole story about this involving a lot of
Pointed homotopy class?
yes, pointed. Everything in this talk will be pointed. There is a whole story about this with lots of work in which I'm neglecting. But I think the place Niall and I decided one should start for reading about this, there's a paper by Attier and Rees, which sort of has a lot of good manipulations in it. It's really good stuff, and I recommend it very highly. Okay. Am I allowed to advance the slides, Dave? Yeah. Cool. Okay, so what does calculus have to do with this? So the point is going to be that, here we have a homotopical interpretation for all rank D complex vector bundles on X. Calculus adds an interpretation for the stably trivial ones. That gives you a good description of that in a homotopical sense. And part of this is just homotopy theory, which is something you can do, but which isn't useful until you get to the calculus. So how does it go? Oh, I think we have this map, BUD to BU, which is the stabilization map we're interested in. Let's just call it fiber fib for now. And then the fiber of that map, well, we've gone all the way around. So the next thing you get to is the loops of the one you started with. That's loops BU or just U. When I hit this with X blank, so I look at base maps from my favorite space X to this thing, then I get this. So this is K0 again. We said BU was the representing object for K0. And if you like, it's a definition of K minus 1, that it's the thing you get by putting the loops on the space before you do it, but it's the next complex K group, and it's, what should I say, it's also a stable object. So what's the point here? The point is that we were interested in stably trivial bundles, in other words, the kernel of this map. And since something like X blank sends fibrations to long exact sequences, the image of this map here is the kernel of that map. So this thing, xfib, is a decent model, first approximation to the stably trivial vector bundles. Of course, it's not quite the same thing, because this map might not be injective. In nice cases, it will be. So for example, if you get lucky and k minus 1 of x vanishes, then it's an exercise with long exact sequences to say that this thing, which in principle has a wraparound map, really is the kernel of that. But I'm sort of going to leave that point there for now. So the point is going to be that we know we care about this based homotopy set, and calculus gives us a name for this fiber. It gives us a good way to talk about it. So how does that go? So here we're going to be doing, and I'm the first person to talk about this. So if you've not seen any of the flavors of Weiss calculus before, I encourage you to just pattern match with things that were happening in Christine's lecture series. So a lot of the formulae will look much like they do for Goodwin calculus. And I want you to take a lot of things on faith and not worry about the details, because I want to, I want to stay focused on what you can use it to say rather than the constructions and what it all means. So there is such a thing as unitary calculus. So this is the kind of calculus which deals with functors which still land in spaces, in base spaces, but they don't take base spaces, they take complex vector spaces. This is a bit of a lie, and this will be important later, but for now, they eat the complex vector space and return a space, and you can do calculus with such things. And in this world, the classical object BUD can be scooped up to a unitary functor. So you think of inserting now any complex vector space V, and then you have a BUV, which, if you like, is the classifying space of the automorphisms in an appropriate sense of that space V. But in particular, if you put our favorite d-dimensional complex vector space CD in, then you get back the classical thing BUD. So BUD, as we know it, is a value of a unitary functor when you evaluate on something in particular. Okay, and then here's a fact. And I'm going to give you a very vague moral reason for the fact. The zeroth polynomial approximation to the functor BU in unitary calculus is the space BU, this space BU, arising as the limit. There's a subtle difference in the fonts, which may or may not be useful as we go along. Very, very vaguely, I mean, this is like BU evaluated at the terminal object, if you like, or maybe it's a pretty good approximation to BU blank by a constant functor. And BU is not a bad one. And what should I say? So I'm gonna talk about something that we don't usually talk about in calculus, actually, but here is like the true object in the story. So I'm going to use D for any functor, which eats a complex vector space and returns a space. I'm going to write D sub closed interval 1 infinity for the fiber of the map that the calculus gives you, which approximates f by its zeroth polynomial approximation. And the reason for the notation, if you know about the way the tower looks, I mean, people have drawn it a few times, but this is some object which is built up of successive fibers, which are exactly the derivatives E1 through infinity, so to speak, of the function you started with. And that's exactly the thing that's showing up here, right? Like CF, the two facts above. We're looking at a map from a value of a unitary functor to the zeroth approximation of that functor, the zero approximation. And then, per definition, the calculus tells us that you can think of that fiber as built up of all of the derivatives from 1 on up, ignoring the zeroth one. And since this power is well behaved, since it converges for BU, there is some dimensional range. I think this came up obliquely earlier. There is some range in which actually all of the there's some range in which this homotopy set is actually just the same as if you thought about D1. The derivatives D2 and so on have not yet started showing up in the picture. They live in higher dimension. They're more highly connected. So there is some range, and I'll make this range precise in a bit, where the base maps we care about, right, the ones that tell us about stably trivial vector bundles in the good situation where this thing really is a kernel and not just a fiber. In a range, the D1 infinity is just the D1, and then the calculus gives us nice descriptions of that object. So we haven't seen this notation yet, I think, but people have said several times that the D1 or the DNs in general are loops infinity of something. You go to spectra and you come back. I find a convenient notation for the thing you had when you were in spectra to be this blackboard bold D1. That's just remembering that this is loops infinity of something that came from spectra. And then by the adjunction between loops infinity and sigma infinity, you can going over to the other side. Why would you want to do this? So now you're looking at a place which, so, you know, I should say F is supposed to be BU here, right? So in good situations, this is where your stably trivial vector bundles live. And it's the same as over here. And over here, you're doing something entirely stable. And this is a calculation in stable homotopy theory, which you can do, and which who does in the paper, and actually, which is the bulk of the work in the paper. We've sort of seen the nice idea that gets you started, and then if you can find out what B1 of BU is, this thing, evaluated in B, where B is C to the D, then, and you can calculate this mapping set, which is in spectra, then you have answered the question, you know, you've at least found a set whose elements are in bijection with these stably trivial vector bundles that you wanted to calculate. And we can't quite see it at the bottom, so let me read it out. But one of the facts that goes into this, which takes, I think, a page or so to prove in the paper, but hadn't been written down anywhere before, that Yang does, is that if you take this spectrum valued version of the first derivative for BU, and you evaluate at C to the D, then the thing you get is, it's not quite, so there's this, there's a D missing on the bottom of the slide. So you can take CP infinity, and there's a map from D-dimensional complex projective space, CPD to CP infinity. The quotient is commonly denoted CP upper infinity lower D. The lower D is the bit that's hidden. And this is called truncated complex projective space. You send that guy to spectra using sigma infinity, and then there's an extra +1 arising as a shift, which has something to do with the fact that you're talking about the complex numbers. Anyway, there is a formula that you can extract for the calculus for what this first derivative is. and you can plug it in, and then it's something in stable homotopy theory, which I won't talk about for the rest of the talk, to try and compute what this set is. So I think this idea is super cool. I think it's nice that calculus showed up organically somewhere it maybe had no right to expect to originally. But does anyone have any questions about that? If I manage to explain this idea well, I'll go home happy, and it doesn't matter what we do doing. Any questions? Go take a drink of water so you can think about it. Again, sorry?
The metastable thing in the.
Aha! Yes. So that's meant to be a vague moral in a metastable range first derivative to control vector bundles. And I'm going to define metastable to be the in a range. The range is the range in which this isomorphism holds. So if you like, it's the minimal connectivity of D2, D3, D4, and so on. I'll be a bit more precise about this on the next slide in the table even. So what kinds of things does Yang prove in this paper? Here are two examples. So since then, Yang together with Morgan Opie and Chatham have done like many more extensions of this idea. And the sort of the direction of extension, since there's a calculation in stable homotopy theory on the end here, is that if you want to push this further, you can just get really good at doing the calculation in stable homotopy theory and bring stronger and stronger methods to bear, and that's what they've been doing, and they've made a lot of progress. But for us, let's start with the sort of the prototypical examples. So why are we doing L-1 rank vector bundles on CPL? Well, if you put the rank any higher, then you're stable. So that would just be a question about K-theory, and since you're asking about, well, we're asking about stably trivial ones here, right? So there would be none. So this is the first case where there's anything interesting to ask. And the theorem says that the cardinality of the set of stably trivial rank L-1 vector bundles on CPL is 2 or 1, depending on the parity of L. And so when I said classifying it, so I suppose it would have been more on the state counting. And then there is this theorem, which I've sort of indicated, but is spelled out in full in the paper. If you go one further, this should be an L-2. I did a careless copy paste. So the next case, the rank L-2 vector bundles on CPL enjoy a 24-fold periodicity, and there's a list of numbers which is given in the paper. This is how many of them there are. Maybe one thing which is interesting to say is if you know what the K-theory of CPL is, then you know that it's made of z's and zeros. So there's nothing in it which isn't in cardinality terms 0 or infinite. So the fact that you actually get interesting counting answers for the stably trivial ones is like telling you that you can actually go back to like a combinatorial invariant and learn something new. I think that's quite fun. Okay.
All right, the way that you compute them, these things are groups. What's the group structure? In that stable homotopy max.
Yes. I don't know. Niall, do you
That's
know?
why they stated as the cardinality rather than telling what you do.
So I get it, but like the thing on the left of your vector isn't obviously a group, right? If you start.
Quite. Yes. I don't know the answer to this question. It has annoyed me several times. So, yeah. Okay. So what do we want to do? We want to ask about realification and complexification. So this is a story. I told you it for complex vector bundles. It works perfectly well for real ones. You can turn a complex vector bundle into a real one just by forgetting the complex structure, and you'll double the dimension by doing so. And then in the other direction, you can take a real vector bundle and maybe I should say induce up tensor over R with the complex numbers and turn it into a complex vector bundle. Okay, I told you at the start that I was brushing some details about what the source category for functors in unitary and orthogonal calculus actually was. This is important here. Something we spent a while tripping over is that you don't actually have an adjunction between the categories that you think about in calculus. So I should tell you what those categories are. In both cases, you don't just take vector spaces for the objects. You take vector spaces with an inner product, and then the maps are supposed to be isometric embeddings with respect to the metric obtained from that inner product. So in particular, they have to be injections. And when you try and run this adjunction, if you have a map from, let me get this the right way around, a real vector space to a complex one, or to something obtained from R, then R is the right adjoint, and you adjoin it across, you make the dimension of the source vector space vector bundle bigger. And something that was an injection might cease to be an injection. So one has to be a little bit careful talking about this as an adjunction. What you can nonetheless do is have these maps R for realification and C for complexification as natural transformations between functors in the calculus. Something which is a bit counterintuitive is that R is now strictly internal to the complex calculus, the unitary one, and C is now strictly internal to the real calculus. This makes me scratch my head every time, but the point is that both of these functors eat a complex vector space and both of these functors eat a real one. So for most of the rest of the talk, much of it, I'll talk about the complex. So here's a table. So I said metastable was supposed to be the range in which the first derivative was telling you everything about these stably trivial bundles, and stable was the range in which everything is stable. And so these, the D here is the rank of your vector bundle over ground field, and dim X is the finite dimensional space that you're thinking of bundles over. I guess dimension as a cell complex. And the ranges are written down here. There's one point I want to draw out of it. We decided wrongly. I don't think I'll have time to get to why this was wrongly. So you can ask me later. But complexification was boring based on this. Let's see if I can do the proof from the table. So you take a metastable real vector bundle. So one whose dimension satisfies this, and you complexify it. That keeps the dimension constant because here we're talking about real dimension and there we're talking about complex dimension. And you'll see that this inequality here is the same as this inequality there. So complexification sends metastable real things to stable complex things. And we were talking about stably trivial metastable things, right? So you land stably trivial and stable. And then I think it's even like a valid syllogism that something that's stably trivial and stable is trivial. So we decided for this reason, but wrongly as it turned out, that there were no interesting questions to ask about complexification. I mean, this was clearly nonsense because people study complexification and have for a long time. But more about that later. Yeah, okay. Last 5 minutes, let's see where we can go. So we thought about realification, and I want to tell you just briefly like a case study on realification and what calculus allows you to say about realification. It's been quite fun. Okay, the slides will get more and more deranged. So very briefly, how the first derivative go. This is really like, I mean, we've seen formulae like this for good calculus. So for it could be for a unitary functor. There's a first derivative, which is a space-valued functor, and that arises as loops infinity of the spectrum-valued version of D1. And when you evaluate that spectrum-valued thing on your favorite vector space, it enjoys this nice formula. So I think many people, have written down formulae like this in different contexts, but the unitary version of it for first derivatives is that there's a spectrum called partial 1 of f that you smash this guy. I can never remember whether it's the 1-point compactification or the regular guy, but it's one of these things with, and then you take the u1, it's the first derivative, homotopy orbits, the formula that Christine was spelling out the intuition for this morning. And since somehow d1 and scripty d1 depend functorially on partial 1, you want to do the calculation there and then try and transport it to the other settings. So we wanted to figure out what partial 1, the map on these first derivative spectra of technical realification was. Times that for 4 minutes. Let's see if we can do it. So many other clever people have calculated what the first derivative spectra on the two sides are. So the first derivative of du as a spectrum is a single suspension of the sphere spectrum. And this is sort of supposed to be a spectrum with an action of u1. So this formula makes sense. The u1 action here is trivial. And likewise, the first derivative of BO, so this line is sneakily happening in real slice calculus. The first derivative of BO is a real thing, is a copy of the sphere spectrum. Okay, so we were asking about not BO, but BO composed R to make it into a complex thing. But there's also a formal formula that tells you what happens when you take the first derivative spectrum of a complex functor that's obtained by taking a real one and composing with realification. And it says, this is as equivariant as I'm going to get. You take the spectrum you had and you induce it up from O1, which is the real thing, to U1, which is the complex thing. So the upshot of all of this is that the map here enjoys this reformulation. Partial 1R is a map in Borel U1 spectra from this thing with the trivial action to this guy, which is induced up from the sphere spectrum with this trivial action. Okay, and then the proposition, which I will just state because I want to tell you somehow where you can go from it rather than how you get there and also provide the bottom, is that so what you then ask yourself what the possible maps are. The possible maps are given by, the homotopy classes of maps in the correct category between these two guys. And the answer is that there's a Z mod 2 worth of maps. So in particular, there's a trivial one and the other one. So this opens up a really actually kind of fun, I kind of like this strategy for deciding which it is, right? If it were the trivial one, then it would be true that in the metastable range, realification sent every complex bundle, stably trivial, to a trivial real bundle. So to show that it's not so, you just have to exhibit one vector bundle that doesn't do the thing. And this is how you do that. So it would be a lie to say this was geometry. What you do is you go and find something that Toda or Mimura wrote maybe in the old algebraic topology handbook, where there's a table of groups which will tell you the answer. So let's go way back to the start. So we said that vector bundles of rank D on any space was mapped into BUD. If I put SK, the sphere, the k-dimensional sphere, then this thing has another name, pi k, unstable pi k of BUD. And there are big tables. There's really a lot of classical work goes into knowing what these groups are. And you can go and look it up, and we did. And one of the things you can learn, I'm sure there are many, 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 many other examples which will witness this for you. But the map from BU2, so rank 2 complex things, to rank 4 real things on pi 5, so we're talking about bundles over the 5-dimensional sphere, is injective. And in particular, it takes this form, with Z mod 2, including as whatever you like in there, Z mod 2 times Z mod 2. So that tells you, going back to here, that the map you're looking at must actually be the non-trivial one. And maybe all I should say to finish is that on the one hand, we do have a formula for it, which I'm not really qualified to interpret, but says that in some sense, this is obtained as a transfer of non-equivariant eta, the map that generates the Z mod 2 in the first stable stem. And I'll just get through maybe what we don't do next also. So there's a functor, gamma, which is the fiber of the map that I've just been talking about. And that's pretty well studied classically. So you can slot the first derivative of gamma into a co-fiber sequence in equivariant spectrum, like so. And I don't know, I would love to know, many people in this room know much more about this than me, if there's a good way of taking a good description of this map and obtaining from it a good description of this spectrum. That would be a nice thing to be able to answer. Okay, that's it, thank you.
Your stable range is where the zeroth derivative controls everything. Your metastable is where the first one. Do you expect further ranges where the nth derivative controls everything for each n?
Yes, and I don't know the ranges off the top of my head, but certainly Greg or Niall will be able to answer these questions for you. So the way the convergence of powers for BU and BO goes is that you say, as you include more derivatives, you get a better and better approximation to the functor itself in the sense that it's more highly connected. So these ranges are just, they're written down in the papers in which these calculi are built and in which these functions are studied. Yeah. Is this that?
I think it's a similar question, but just to be sure, I'll ask it again. So from what I understood, the reason calculus appears is because of the computation of P0 being like happens to be this very interesting space for comparing non-stable things to stable things.
Yeah.
And I don't know anything about this orthogonal and unitary calculus, but would there be reason for P1 or P2 to appear in terms of computations of P1 of BU, P2 of BU, and could then the higher PNs say something about this question?
As far as I know, no. So I mean, it may be the case, but my best understanding of the story is just the interpretation. The answer comes from P0 and the ability to compute comes from D1. And it's that push pull that's sort of all there is in town, yeah. But I might be wrong.
In the beginning, when you introduced the classifying space, you said that the isomorphism classes of vector bundles correspond to the homotopy classes of maps into the classifying space. Is there some way to describe the morphisms between the vector bundles through homotopies between things into the classifying space or some other way in the classifying space?
I feel there ought to be, but I've never actually thought about this. So anyone in the room who has an answer, please give.
I know that for principal group bundles, it's true for discrete groups, but not true for other groups. So I wonder how it is for vector groups.
I don't know.
Something straightening, That's the answer.
Thank you, Con.
Any other questions? No, we should, thank you.